For a brief moment, just a few weeks, a single dying star can outshine an entire galaxy of 200 billion suns. It releases more energy in that moment than our sun will produce in its entire 10 billion year lifetime. A shockwave of gas and radiation expands outward at 30 million kilometers per hour, tearing through everything in its path. This is a supernova, and without it, you would not exist. Last time, we watched stars like our sun quietly fade into white dwarfs, a gentle, gradual ending. But for the most massive stars in the universe, there is nothing gentle about the end. Today, we're talking about the most violent events in the cosmos, and why these catastrophic explosions are responsible for almost every atom of heavy material in the universe, including the ones inside your body. A supernova is a stellar explosion, the violent, catastrophic death of a star. Not all stars end this way. As we saw last video, stars like our sun go quietly, expanding into red giants, puffing off their outer layers, and leaving behind a white dwarf. But for stars with significantly more mass, roughly 8 times the mass of our sun or greater, the ending is anything but quiet. There are 2 main types of supernovas, and they happen for completely different reasons. Let's look at both. Remember how stars burn hydrogen in their cores? And when hydrogen runs out, they start burning helium? Massive stars keep going further. After helium, they burn carbon, then neon, then oxygen, then silicon. Each stage produces a heavier element and lasts a shorter time. Burning hydrogen takes millions of years. Burning silicon takes just a few days. But then the star reaches iron, and iron is where everything stops. Every element up to iron releases energy when fused, but iron is different. Fusing iron actually consumes energy instead of releasing it. So when iron builds up in the core, fusion simply stops. There's no more outward pressure to counteract gravity. The core, which at this point is roughly the size of Earth, collapses in less than 1 second. In that fraction of a second, the core is compressed to the size of a city. Densities become so extreme that protons and electrons are crushed together into neutrons. The collapse suddenly halts. The core has become a neutron star, and it's so rigid it bounces. The bounce and the blast. That bounce sends a shock wave rippling outward through the rest of the star at a significant fraction of the speed of light. The shock wave slams into the star's outer layers, billions of kilometers of gas, and blows them apart in an explosion of almost incomprehensible scale. The star's outer layers are flung into space at up to 30 kilometers per second. For weeks, the explosion glows brighter than anything else in the galaxy. Then, slowly, it fades, leaving behind an expanding cloud of debris. And a neutron star, or sometimes a black hole, at the center. Sound familiar? This is exactly how the black holes we discussed in previous video are born, from the collapsed cores of the most massive stars. The second type of supernova has a very different origin story, and it starts with the quiet white dwarfs we met last time. Some white dwarfs don't exist alone. They orbit a companion star in a binary system. If the companion is close enough, the white dwarf's gravity begins to pull material off it. Hydrogen gas slowly spiraling down onto the white dwarf's surface. The white dwarf grows heavier, and heavier, and heavier. There's a limit to how much mass a white dwarf can hold, called the Chandrasekhar limit, at about 4 times the mass of our sun. When the white dwarf crosses that threshold, it triggers a runaway nuclear explosion that tears the entire star apart in seconds. Unlike a core collapse supernova, there's nothing left. No neutron star, no black hole. The white dwarf is completely destroyed. Why type Ia supernovas are cosmically useful. Here's something remarkable. Every type Ia supernova explodes with almost exactly the same brightness, because they all happen at the same critical mass. This makes them what astronomers call standard candles. If you know how bright something truly is, and you measure how bright it appears, you can calculate exactly how far away it is. Type Ia supernovas have been used to measure the distances to galaxies billions of light years away, and they're the reason we discovered that the expansion of the universe is actually accelerating. A discovery that earned the Nobel Prize in Physics in 2011. The remnants after a supernova, the expanding cloud of debris, is called a supernova remnant. These glowing shells of gas can stretch for dozens of light years, expanding outward for thousands of years after the explosion. The Crab Nebula, one of the most studied objects in the sky, is the remnant of a supernova observed by Chinese astronomers in 1054 AD. It's still expanding today, nearly 1,000 years later, the elements that make life possible. But the most important thing a supernova leaves behind isn't the neutron star, or the black hole, or even the glowing remnant. It's the elements. During the explosion, the extreme temperatures and pressures forge elements heavier than iron, gold, silver, platinum, uranium, that couldn't be created any other way. All of these elements are blasted into space and mixed into the gas clouds drifting through the galaxy. Eventually, those enriched clouds collapse into new solar systems, with planets made of iron and silicon and carbon and oxygen. Planets like Earth, the gold in your jewelry, the iron in your blood, the calcium in your bones. All of it was forged in a dying star and scattered by a supernova billions of years before our sun even existed. The star that has everyone watching. Here's a question people ask a lot. Will we see a supernova in our lifetime? Possibly. And there's one star in particular that astronomers are watching very closely. Betelgeuse, the bright reddish star in the shoulder of the constellation Orion, is a red supergiant nearing the end of its life. In 2019 and 2020, it dramatically dimmed by about 35%, causing a wave of excitement and speculation that it might be about to explode. It turned out to be a massive ejection of surface material that temporarily blocked its light. Betelgeuse is fine, for now. But when Betelgeuse does finally explode, it will be visible in broad daylight. It will be as bright as the full moon. For weeks, it will cast shadows at night. It's located about 700 light years away, far enough to be completely safe, close enough to be the most spectacular astronomical event in human history. Astronomers estimate it could happen any time in the next 100,000 years, which in cosmic terms is extremely soon. In human terms, we might just have to wait. We'll dedicate an entire video to Betelgeuse soon. Stay subscribed. Supernovas are destruction on an almost incomprehensible scale, but they are also creation. Every heavy element in the universe, every piece of every planet, every molecule of every living thing, was forged and scattered by these cosmic explosions. Without supernovas, the universe would be a cold, dark place, filled only with hydrogen and helium. No rocky planets, no water, no carbon, no life. The violence of a dying star is the very thing that makes the existence of life possible. Next time, we'll look at what supernovas leave behind. Neutron stars and pulsars. Objects so extreme they make black holes seem almost ordinary. If this video earned a like from you, thank you. It genuinely helps the channel grow. Subscribe if you're new and drop a comment. Which supernova fact hit you hardest today? See you in the next one. Keep looking up.